Hello everyone, welcome back to my channel. So, in the last class, we started a new series on finite difference methods, and I told you that most of the finite difference methods, at least that I know of, they originate from what is called as a Taylor series expansion. So, we considered the example of a one dimensional grid, that is, one dimensional set of points. We set a reference point to a location that we labeled as x of I, that is the physical location that it represents is x of I, and a neighboring point which has the location of x of I plus 1. So this subscript I plus 1, it's just a convenient measure to count the number of grid points, and it's usually called as an index. We were interested to look at a variable, that is phi, which is developing in this one dimensional space, and we said that the variable phi has the value of phi of xi at the location xi, and the variable phi has the value of phi of xi plus 1 at the variable location xi plus 1. So nothing too significant so far. So going back to the high school, we recalled that the Taylor series expansion, if we choose the reference point as xi, and if we want to get the value of phi of xi plus 1, then this can be computed from this particular series over here. So one important thing that I probably forgot to mention is that for this Taylor series expansion to work, phi, it must be continuous and differentiable. So this is a very important preliminary requirement for the Taylor series expansion to work. Without this, we will not be able to figure this out. The reason is because we have these derivatives appearing in the Taylor series expansion, and these derivatives are not going to work if the function is discontinuous or not differentiable. So having said that, this is an important due diligence that I had to get it out. Otherwise, somebody might say that this is an important piece of information that I hadn't considered. So using this Taylor series expansion, our aim was to obtain the first derivative of phi at the location xi. So in all the discussion that we would do, this xi is our reference location. So we want to get the derivatives at the reference location, and the reason why we are seeking these derivatives is because the kind of differential equations that we would be considering, these are either going to be partial differential equation or ordinary differential equations, and they would usually contain a first derivative term or a second derivative term. So the main objective of this course is to provide you with a set of tools and techniques so that you can consider or you can evaluate how to get these first and second derivative terms using the finite difference method. So we understood that, and we wrote the Taylor series expansion. We understood what our aim was, that is, we want to get this particular term. So we simply rearranged this entire equation, and we said that if you want to calculate the first derivative of phi at the point I, you can do so if you can calculate all these different terms on the right hand side, which are a part of infinite series. So now the question comes, do we really know that as to how we can evaluate all these different parts? So the answer is maybe or maybe not. And the reason is because on the right hand side we have all these derivative terms, higher order derivative terms that are sitting. So in most likelihood we don't really know the information of these higher order derivatives, given the fact that we are evaluating or we are trying to evaluate the first derivative. So while this particular equation, which is nothing but an exact value of first derivative, if we consider all the different terms in my infinite series, so we surrender ourselves here, and we say that we don't really know what all these different higher order derivatives are. So why don't we just truncate the series somewhere, or in this case we truncate the series here, and we say that this particular part where we had truncated is going to be an approximated version of the first derivative, and all these terms that we have neglected, these are going to be what is called as a truncation error. So this is something that we looked at in the previous class, that this is finite difference based approximation. So this is not equal, this is probably an approximation, and the approximated version is the red term over here, and in the yellow we said that all the different terms that we truncated would contain some sort of error in this approximation. And to represent that approximation, or to represent that error, we understood the first fact that we consider the delta x to be a small quantity. And when we say small quantity, it means that delta x is much smaller than 1. And if that is the case, then for any integer value, any positive integer, we say that the delta x raised to power n is going to be greater than delta x raised to power n plus 1. So to give you an example of this, if this is the case, then delta x would be greater than delta x squared, and similarly delta x squared would be greater than delta x cubed. And this is only going to be the case if and only if the delta x is a small quantity lesser than 1, which is ideally true for almost all the CFD problems, or almost all the computational mechanics problem that I have worked with. So having understood that, we compare the term number 2 and term number 3. We say that this term has a coefficient of delta x by 2 factorial. So if I ignore the 2 factorial, it means that the coefficient is delta x, whereas the coefficient over here is delta x square. So one may say that this term may be larger than this if these derivative terms are not going to play a super important role, or if these derivatives are not ridiculously large, then we can say that the delta x term over here would be larger than delta x square term. And that is what we are going to sticking with. We are assuming that these derivatives are not exponentially large as they take on higher order powers, and therefore the first term over here would be larger than the second term. So all the different terms that we have truncated, it is very likely that this particular term contains the largest magnitude, and the largest magnitude term contains delta x in its coefficient, and that is why we say that the order of the truncated error, or the order of the error that is associated with the truncated terms, contains delta x as the primary source. And it basically means that if we reduce the delta x, then error would be approximately reduced by a factor of delta x. Okay, so we'll see with the help of a demonstration later on after all this theoretical discussion. But right now it is important to understand how this delta x basically comes in. So this delta x is a manifestation of the largest term in the truncation error. Okay, so this was one of the examples of how we can use Taylor series expansion to come up to a first order approximation using finite difference method. So in this, we had considered our reference point here and the neighboring point on the right hand side. So one can also take up a very similar case. So let me just copy this entire thing and let me give you a slightly different argument. So we'll take all the things here and I'll just remove all this. Okay, I'll say that instead of considering this point as delta x or xi, not delta x, instead of considering the reference point here, what if I switch the location? I say that this is my xi and therefore this is my phi of xi, right? So this is a possibility. If we have a grid of points which are more than, let's say, 3, then this is a very valid possibility. And in that case, if I go by the idea of counting, then this particular location would be x of I minus 1 and this point would be phi of x of I minus 1. And here I can write delta x So if we stick to the original notation, so this would be called as delta x I minus 1 equals to x of I minus x of I minus 1. Okay, so this is a very valid possibility, but we are sticking to the fact that we are fixing, or we are going to fix we are going to fix xi as my reference point. So now what we are going to say is, we know the values of xi minus 1 and xi, and since xi is our reference point, we know what is the phi of xi. Then the question comes, can we evaluate phi of xi minus 1 using the Taylor series expansion? And the idea is very similar. So previously, the reference point we had was on the left, and the neighboring point was on the right hand side. So we were moving in the positive x direction. This time the situation is slightly flipped. The reference point is here, the neighboring point is on the left hand side, is in the negative x direction. So essentially what we can do is, if we replace the delta x contribution as basically as minus delta x, that is, we are going in a different direction, we can come up with the same kind of series that we had begin with. So to demonstrate that, I'll just copy this entire thing so that I don't have to write it, and you can understand how the original Taylor series would be modified, which is, I think, more important rather than my laziness here. So okay, let's look at it one by one. So it is important to see that the xi is my reference point, so this is fine. All these derivatives are fine because all these derivatives are evaluated at the reference point. So what we are seeking is phi of x of I minus 1. My reference point is fine, and now since I mentioned that the distance that we are moving is, instead of delta x, we are going to be moving a distance of minus delta x. So this term over here would change slightly. We'll be going with minus x of I minus x of I minus 1. So notice that this particular bit is my delta x I minus 1. Okay, so this is going to be the case because now we are moving in slightly different direction. So previously we were moving in another direction, that is in the positive direction, but now we are going to be moving in the negative direction. And similarly, this particular numerator, it would be xi minus 1 divided by 2 factorial, and we are going to retain the positive sign here, since if we do the square of a negative entity, it essentially becomes positive, right? And the general term that we have, which is, I think, the most important part for you to understand what is going on. So the general term over here, it would be xi minus 1 raised to power n divided by n factorial, but there would be another term over here which is simply minus 1 raised to the power n, and this is because we are moving in the negative direction. I hope that this is clear. If this is not, just try to do this thing by yourself as to how we can choose a different reference point and move in a different direction. It is not very tricky, but it just needs a little bit of patience and understanding to completely get this picture. Again, now that we have written this, our aim is to get the value of del phi over del x evaluated at the point I. So I'm using these partial derivatives here, assuming that this phi could be multivariable. If this is a single variable, this would simply become d phi over dx. I think in the previous case I was using both of them interchangeably. So just keep in mind that this is going to be a multivariable problem later on. So that is why I'm keeping with the partial derivatives. So again, if we look at the Taylor series expansion, it is not very hard to understand that we can evaluate the variable del phi over del x at the point I just by tweaking some things here and there. It simply means that it phi of xi minus phi of xi minus 1 divided by x of I minus x of I minus 1. And this time the first term here would be x of I minus x of I minus 1 divided by 2 factorial multiplied by the second derivative and so on. And the third term would be a negative this time. It would be xi minus 1 squared over 3 factorial times the third derivative. So I'm simply writing phi triple prime and subscript of I, which represents that it is being evaluated at the ith location all the way up to infinity. So this scary looking expression is the exact formulation. Remember that since it's an infinite series, so it is going to be an exact formulation. Again, we are going to succumb to the fact that know that we are trying to evaluate the first derivative, so it is very unlikely that we know what is the second derivative, third derivatives and so on. So again it needs that we are going to truncate the series somewhere. So we can truncate even after first term, we can truncate after second term. That is up to us to decide based on our judgment. So the judgment is we don't know the second derivative, so we have to truncate it over here. So in that case, what we end up with is del phi over del x evaluated at the location I, that is my reference location, is approximately equal to phi of xi minus phi of xi minus 1 divided by xi minus xi minus 1. This is my approximation, and now I had truncated my series until here, and all of these terms that I'm trying to currently highlight, these are the terms that I have truncated, and these would give rise to what is called as a truncation error, just like before. And just like before, we are going to assume that delta x is a quantity which is smaller than 1, or it could be much smaller than 1, but it is at least smaller than 1. And if that is the case, then the magnitude of this term is going to be larger than the squared terms and so on, which again indicates that the first term in my truncated series would be the largest, given that the derivatives don't take crazily large values at any point. This is an approximation, and therefore the terms that I am truncating, and knowing that the first term is going to be the largest, we say that the error for those truncation term would be of the order of delta x. And this order basically means that it has a magnitude proportional to delta x, and that essentially means that when we reduce the delta x, the order or the error that we have in this truncation series, so the truncation error, not just the error, it's the truncation error, it moves down in the same proportion. So if the delta x is reduced by 2, then the truncation error would also reduce by roughly a factor of 2. And on the vice versa, if delta x is increased by a factor of 4, then the truncation error would also increase by approximate factor of 4. So that is the basic idea of this truncation error. So this is the expression that we end up with, and this expression is an approximation. So notice how we move from an exact formulation to approximation of the first derivative. Approximation of the first derivative. So now we have derived two different kind of approximations. So I'm just trying to hold my screen here. So we have derived two different approximations to the first derivative, and they approximate look very similar to each other. The truncation error is also very similar, but there is a very small tweaking that we had done. So in the first case, we considered the reference point here, and the second point that we were taking the help of with was in this positive direction. And in general, in the finite difference terminology, this positive direction is basically called as a forward direction. So this is called as a forward direction. So if we are going in this direction, it is considered as a forward direction, and that is why the approximation that we had derived in the last lecture was called as a forward difference method or forward difference scheme. So surprisingly, the acronym is again same as the finite difference method, that is FDM. So just don't get confused. If somebody just uses FDM, it could be finite difference method or it could be forward difference method. So the key takeaway here is that in the forward difference method, our reference point is slightly behind. That is, the neighboring points are lying in the forward direction only. Whereas the approximation that we did today, the reference point is sitting here and the neighboring points are going in the opposite direction or in the negative direction. And again, I think you might have guessed it right, that this is called as a backward estimates. So the scheme that we have derived today is called as a backward difference scheme or backward difference method. So you can probably use either name, that is totally fine. But the key takeaway here is that at least for the expressions that we have derived, the truncation error is approximately the same. So in both of these expressions, the truncation error, which is probably the most important aspect of these approximations, is of the order delta x. So in finite difference methods, so let's say, so we have finite difference methods. So finite difference methods, we want to get the information about the derivatives. So far we have looked at the first derivative information using forward and backward differencing scheme. And in their most basic step or in their most basic formulation, these errors, these estimates had an truncation error of the order of delta x. So in the next lecture, we would take this one step forward and we would come up to what is called as a central difference scheme, which is probably more widely used as compared to this forward and backward, but it is important to know the background of forward and backward differencing scheme. So this is usually just written as CDS. So we would look at how we can get the information about the first derivative using the central differencing scheme. And one final remark that I would like to make is, in the classes today and the before, we have derived the forward and backward estimates that had a truncation error of delta x, but we can come up with more advanced formulations in which the truncation error is even smaller. So I hope you would agree that if the truncation error has delta x square, then this would be smaller as compared to delta x, comparatively to delta x, right? So there are ways in which we can derive the forward and backward difference estimates that have the smaller truncation error, but that is slightly advanced. So we'll keep that for a slightly later classes. First, our idea is to get the basic estimates of forward difference, backward difference and central difference. Then we will look at how these estimates actually work out in some applications, some simple applications. And there we would also look at what is this entire fuss about the leading term error. Okay. So I hope that this discussion would give you some better sense of finite difference methods, especially the backward difference methods as of today. In case if there are any questions regarding the backward forward difference method that we have covered so far, or if you have some burning question about finite difference method, I can try to take that up If I don't know, then I'm really sorry about that. But if you in case if there are questions, please write it down in the comments. I will try to address them as soon as possible. Once again, thanks for being patient and listening to my rant. I hope you learned something out of that. Very shortly, I'll release another video about the central difference method. Until then, take care and bye bye.